cloud. Okay. Thank you. So, yes, so let's continue. So in Newtonian mechanics, we have this Newton's law, that is mass times the acceleration is equal to the force at the point where we measure the acceleration. And if q of t is a trajectory, then the first derivative in time, which is usually denoted by q dot, is the velocity, and the second derivative in time is the acceleration. So what it means is that Newton's law gives us second order differential equation for the evolution, for the trajectory of a particle. And if we will supplement this differential equation with the appropriate boundary conditions or initial conditions, then this fixes the trajectory. So initial conditions, that's q0 is fixed and q dot 0 is fixed. So we fix the coordinate and the velocity, and then this determines a trajectory of Newton's point particle in the vicinity of time equals 0, where the solution exists from the mathematical point of view. So this is the initial condition. We can also impose these sort of ballistic boundary conditions. That's when we fix the initial position and the position at the target, Q2. And then in good cases, it fixes the trajectory uniquely. In some other cases, it might not fix it uniquely, but so in good cases, it's uniquely fixed by the initial and the target position. Okay, very good. So, but then we have a special class of potentials. Sorry, special class of forces, potential forces. That's when the force is equal to minus the gradient of some function of q. So this function can be smooth, can be nice, can have some singularities. Well, you shouldn't worry too much about singularities because the, say, for example, Coulomb potential, it's whatever this the charge over the distance from the center. So it's well, I'll just put, this is not really a physics course, this is more mathematics course, so I'll just put some constant c. So you can see that Coulomb potential has a singularity at q equals 0, and depending on whether it's attractive force or repulsive force, this singularity will be either plus infinity or minus infinity for the potential. So, but it's important that it's a potential force. So I'm looking at my notes because I may forget something important. Okay, so when we have a potential force, and this is the case which we'll be studying throughout this course. So in this case, two good things happen. First, for potential forces, Newton's equations plus boundary conditions, I will not specify exactly for which boundary conditions this will be true. So when I say boundary conditions up until a certain point in the class, I will always mean these boundary conditions, that we fix the initial point and the target point of the trajectory. So for potential forces, Newton's equations plus boundary conditions can be described as critical points of a functional, action functional. And we have this very powerful description of trajectories as minimizers of certain functionals. So the other thing that happens for the potential forces is that there is at least one conservation law. The quantity q dot squared divided over 2, no, sorry, plus uq is constant along each trajectory. And the meaning of this quantity is the energy, and this first part is the kinetic energy, the second part is the potential energy. So these are the two special things that happen for potential forces, and we will stick to the case of potential forces. So now, what is this action function? So I'll jump ahead and I'll say that the first property is basically the essence of Lagrangian approach to mechanics or Lagrangian mechanics. So the fact that you have conservation laws is more natural in the other formulation of the same mechanical problem, Hamiltonian mechanics. And jumping ahead to the quantum mechanics, I should say that for quantum mechanics, the most important thing is Hamiltonian approach. But in this first part that concerns the classical mechanics, we will discuss both the classical and the Lagrangian and the Hamiltonian approach. Okay, so what is the Lagrangian approach? Lagrangian formulation of classical mechanics. So far, I will restrict myself to Newtonian case. And then we will see how to extend this to kind of more general settings. How to extend it to more general settings and why to extend it to more general settings. So first, Newtonian case. Let's consider the functional that is called the action functional. It's a functional on the space of path, of parameterized path in R3. So let's call, so it's a functional on P T1, T2, which is the space of parameterized path in R3. It's the same as mappings gamma from T1, T2, the interval, to R3. Unless we will need something dramatic, I will always assume that these paths are smooth. In other words, they are differentiable sufficiently many times. Okay, so this is the action function. You probably know this principle, I think it's attributed to Lagrange, but I don't know well the history of mathematics. So it's the minimal action principle, and it's sometimes it's elevated to the philosophical concept sort of minimal action principle. So here, this is a very specific thing. It's not minimal, it's the critical point. So let's describe critical points. I'll check my, okay. No, it's, I'll be checking the phone because sometimes people cannot get in and they would call. So let's describe critical points of this function. Well, first of all, what is a critical point?
By the way, what is like a topology or any other properties of the space of all smooth paths, or we are not using only smooth paths, but partially smooth? I don't know how to say it.
Yeah, let's say the following. Yeah, I will move as fast as possible through the material, meaning the, you know, if you will try to stick to some very rigid framework, mathematically rigid framework, at any of these points, the motion will be extremely slow and counterproductive, because you know, many things depend on how well you define the object. So let me be very vague here. So this is a space, it's a topological space of smooth mappings from the interval to R3. You may ask, what is the topology here? Well, as usual, in the space of mappings, you can invent 100 topologies. So let's just wait and let's see if we need any topology. And then, or rather, to these more sophisticated questions, I will, my answer will be the following. I will refer to a good textbook on variational calculus, on the calculus of variations. And there is a full discussion of topology. So we're just moving as fast as possible through these notions. Our goal is really to pass to quantum mechanics with full understanding how classical mechanics is deformed into quantum mechanics. All right, so first, what is a critical point? As in case of functions of n variables, a critical point is where all derivatives all partial derivatives are vanishing. So the question is, what are partial derivatives in this case? Well, it's the following. Let's take, so we have, suppose we have a path gamma. So then let's consider it's one parametric deformation. So let's say that gamma is gamma 0, this is gamma 1, and we are deforming this path, including the boundary points. So somewhere in between there is a gamma s, and gamma s is it's a mapping from, well, I'll define it first like this. So it's a mapping from T1, T2 cross 0, 1 to R3, rather gamma. And gamma s is a path which it's a parameterized path again, but now it depends on s, T1 to T2. Okay, so then if it's a smooth deformation, if we will differentiate this family at s equals 0. So this is, so what is this? So eta now is a mapping T1, T2 to R3 as well. But it has a different meaning. So eta now is a tangent vector to the space of this path. How did I denote it? T1, T2. At the point gamma. So now we want to have a critical point. So
you mean we have a trajectory of paths in our space, and eta is a tangent vector to this trajectory. It's a curve.
it's a tangent. No, it's a. You see, you have the space of path.
Yeah.
Full space of path. I mean, let's imagine that it's a smooth space. So, but it's an infinite dimensional space.
I mean, variation of a path, it is a path in the space of paths again.
Yes, exactly.
Yes, and we have an eta is a tangent vector to this path.
Exactly.
Okay.
Yes. So very good. So then, so now I want to define the directional derivative. In the direction eta of our functional S. And it's the most natural thing you can imagine. You take this family of paths and you differentiate the functional at S equals 0. So if you will do this, what are you going to have? Well, this is our action. So we have to differentiate q dot squared, and then we have to differentiate u of q. So the result will be from the first term we have this, and then the derivative of q dot in S evaluated at S equals 0 will be eta dot t minus, and then we use the chain rule. So we have the gradient of u scalar product with the direction eta dt. Very good. So sometimes it's called the variation of S at gamma in the direction eta. And really, when you see or when you see a variation somewhere written, or when you hear this is a variation of something, it simply means a directional derivative. And this variation eta, which sometimes is denoted by delta q, especially in physics literature, this is simply a tangent vector to the space of path. And here we consider the very simple case when these are paths with the values in a vector space R3, then the variations are also the same kind of path. If we have some manifold, and if our gamma is a path in a manifold, then the nature of eta will be different. We'll take values in tangent space of this manifold. But anyway, so this is what we have here. So now we can write this variation and simply by integrating, using integration by parts in the first term, we can write it as minus eta t, and then n q double dot t minus plus the gradient of uqt dt from t1 to t2. But then we integrate by parts, so we pick up boundary terms. So m q dot t eta t between t1 and t2. Okay, so so now you can see that delta eta s gamma is 0 for all eta, if and only if in the bulk, meaning when t is strictly inside of the interval, we must have the differential equation, which is exactly the Newton's differential equation. For qt in the bulk. But then we also have boundary terms. So we should have m q dot t1 eta t1 minus m q dot t2 eta t2 equals 0. So this is Newton's equations. And now what is this? Well, these are certain conditions on the variation. So in order to understand these boundary terms better, we need to analyze boundary conditions. So we will do it in the Hamiltonian framework because there it's more natural. Let's look back over here. And this is where I mentioned boundary conditions for the first time. And remember, we want to impose boundary conditions in order to fix the solution. So let's impose these boundary conditions. So let's see that there is a bijection between solutions to Newton's equations with boundary conditions, Q1 and Q2, and the this critical points of the action function with the same boundary constraint. So now assume that QT1 is fixed, let's say by Q1, QT2 is fixed by Q2. Since Q at the boundaries is fixed, so when we do the variation, we can only vary this path inside the interval T1, T2, not at the boundaries. At the boundaries, everything is fixed. So it means that for this boundary condition, the boundary value of the variation is 0, which means that boundary terms vanish. And so we proved the following theorem, that critical points of S of gamma with, I will call this Dirichlet boundary conditions. With Dirichlet, I mean, it's clear why it's Dirichlet. Boundary conditions are in bijection with solutions to Newton equations with the same boundary conditions. Okay. So this is the variational principle in classical mechanics. This is the Lagrangian mechanics. So so here is the natural homework. First, find solutions to the, I will call it Dirichlet problem. For Newton's equations, for first zero potential, that's free particle. This is easy. Second, it's harmonic oscillator. You can see that it's spherically invariant, rotationally invariant harmonic oscillator. And finally, Ij, Qi, kappa Ij, Qj, where kappa is some symmetric 3x3 matrix. So this is the asymmetric harmonic oscillator. And second problem, find critical values of the action function. We will use the second homework. We will use this in the semi-classical analysis in quantum mechanics. Okay, so so this is the Newton's story of a single particle in R3 in a potential force. But now we know that it's a rare event when we have a single particle. In any reasonable system, we have many particles. So let's look at n particle. N particles when moving according to the Newton's law. In this case, let's say we have n point particles with masses m1, mn in a potential force with the potential u, q1, qn. Q1, qn are positions of our particles. So then Newton's law tell us that for particle number A, it's very unfortunate that I use the same letter for the acceleration and for the number of particle. Mass times the acceleration is equal to the total force acting on the particle, since we agree that it's a potential force. So we take the gradient with respect to the position of this particle. So it's this. This is the Newton's law. It gives it gives differential system of nonlinear system of second order differential equations. And these are the equations of motions of our system. So it's a simple exercise to see that similarly to a single particle, it can be written as a variational principle. So the Lagrangian formulation the action is very similarly, but now gamma is a collection of n paths. So now gamma is a mapping from T1, T2 to R3 to the n. And the action is just sum over A from 1 to m to n, mass, velocity squared over 2 minus u of all these q's that depend on t. Okay. So, and again, you can easily see that we have a theorem. It's a nice exercise to prove it. It's an elementary exercise to prove it, just by analogy with what we already did, that critical points of S with boundary conditions QA T1 is equal to, let's say, QA T2 is equal to Q capital A in bijection with solutions to this equation, to the Newton's equation. With the same boundary condition. Okay, so so this is easy. If this is not easy, if you have questions, feel free to interrupt and to ask questions. Okay, now some special cases. Well, naturally, when the potential is the sum of potentials that depend only on the 8th coordinate QA, so this is these are particles in an external potential force, but particles don't interact, non-interacting particles. And say if we add some terms like this, sum over A, B, U, A, B, Q, A, Q, B, let's say A less than B, in order to avoid repetitions. Then these potentials, they describe particles in an external field with pairwise interaction, which is given by these potentials. And so on. You can imagine some situations in chemistry where you have the interaction of three particles and so on, but typically in any physically relevant models, two particles interactions, they describe everything that's needed to be described. So now I mentioned manifolds at the very beginning. So why manifolds? So far we are quite happy with R3. But imagine the following situation. So now new chapter, constraining potentials. So imagine a situation when, say, let's consider an example. So we have R3, and we have a potential that's a function, real valued function on R3, and assume that it's spherically invariant. And it's like a deep well in the radial direction. So here we have radius r, and along this axis, if we go, so the function u is spherically invariant. So what's relevant is how it changes in the radial direction. And I assume that it behaves like this. Near the radius, so this is the sphere of radius r. And then we can consider a family of such potentials that become deeper and thinner. And so now suppose that we study particles moving in this potential. And let's assume that it's sort of trapped inside of these walls. So then it will be moving like this. And this distance, epsilon, let's say that we have a family of these shrinking potentials epsilon. And this epsilon goes to 0. So the potential is shrinking and shrinking in width. So at the end of the day, when epsilon is 0, and I don't have the guts to say epsilon is 0 because it's really the limit, epsilon to 0. Particles are trapped on a sphere. Or rather, we have one particle is trapped on a sphere. So at the end of the day, we have particles moving on a sphere. And this means that we constrained our particle to some submanifold in R3. And it can be done in a different way. Say, imagine that you have, say, 4 particles. So 4 particles with pairwise potentials UAB, QA, QB, pairwise potentials. And let's assume that these potentials are of this form that's supported on a sphere. So then you're fixing the distances, let's say 1, 2, 3, 4. So now you end up with the structure where these distances are fixed. And so you can see that it's a tetrahedron, but it still can move. It can rotate like this. So this is how the these ideas, which are mechanically very natural, because I mean, imagine that you have some construction from rubber bands, then they can move, but then you freeze this construction, and the rubber becomes solid. So, and then after you freeze it, it becomes a solid body. So more or less, this is how you can naturally pass from the mechanics of particles in R3 to the mechanics of solid bodies. And what does it mean, solid bodies? It means that the degrees of freedom of these solid bodies, they form some manifolds, possibly with singularities, but we will not pay attention to the singularities yet. And so this is called constrained motion. So constrained motion. And where this constrained motion is, it's on some surface S in our space that we started with. And this is how you end up with, so then the question is how to find Newton's equations for these limiting solid bodies, or for this limiting motion on S. And it's time to have a short break. Let's have 5 minutes break. If you have any questions about this material, so feel free to ask now. It's a good time to do it.
I have a question about n particles mathematical model. Is it possible to generalize it to the infinite number of particles in such a way that only finite number of particles could how to say it? So in the previous example, we considered the case when the particles are pairwise interacting, and in the settings of infinite number of particles, we could consider we could require that only finite number of particles could interact.
Yes.
And
yes.
The more particles involved in an interaction, the lesser coefficient of this interaction is
you're making it very complicated. Let's assume that all interactions are pairwise. So let's assume that we have this potential. Let's assume there are no external forces. So this potential is just sum over A less than B, UAB, QA, QB, and the number of particles goes to infinity. And then and it's a beautiful subject in statistical mechanics, which is called the theory of kinetic equations, Boltzmann equations, and all this stuff. It describes the motion of, say, liquid or of gases. And then when you pass to this limit, I mean, you really have to be guided by physical principles. What do you want to achieve? Say, if you want to have the gases with low density, then n goes to infinity, but the volume of your system is much bigger than n. If you want to have a big density, then you consider your particles moving in some kind of constrained space, and the density of particles in this constrained space is finite. So it's a beautiful subject. You see, as n goes to infinity, there is this. So then, yes, so then the philosophy of Newtonian mechanics is becoming sort of questionable. Questionable in which sense? If you ask a philosopher, what did Newton taught us? A philosopher would say, I mean, sort of, the philosopher who cares about it, he would say, he taught us the principle of determinism. So we have the initial conditions, and then we have Newton's equations, and everything is determined. So, like, I think it was Laplace that says that, give me the initial conditions and I will predict the future of the universe. It's very naive because the problem with differential equations, as we know it quite well, is the following. Many differential equations are unstable. So if you run the solution for a long time, small variation in initial conditions will give you huge variations in the outcome. And so when you increase the number of particles, these small variations in the initial condition, they basically destroy your solution after 0 time. So there is no deterministic way to describe this, these ensembles. The only way how to do it is to say something like this, that instead of, so we consider these QAs as point masses of the distribution. So now instead of describing individual particles, we will describe the, distribution supported at these points. And instead of the evolution of individual particles, we will consider the evolution of this density. And then as n goes to infinity, it's a big science. It's a huge science. It's, say, one of the Fields medals in 2010 was given to this French guy with the spider. I forgot his name. He's very famous. He is now the a big politician in France. So he got this medal for studying kinetic equations, basically for studying these questions. It's a very big subject in non-equilibrium statistical mechanics. So
Yeah, thank you.
You have a good question. I don't have a good answer. Any other questions? Okay, so let's move on. So, so what did we? Okay, so the conclusion is that by considering the sequences of these potentials, these constraining potentials, we can constrain the motion of our particles to the motion on some submanifold in Rn. And now the question is how to derive the equations of motion for in this case. Well, that's where the variational principle is very useful, because for any intermediate value of the potential, let's consider an example. I don't want to, so we will just develop the variational principle for general configuration spaces, for general submanifolds, maybe a little bit later, but now let's consider an example. So assume that, yes, let's just finish this example. So we have the potential that's constraining our particle in R3 to a particle moving on a sphere. So now as epsilon goes to 0, the particle moves on a sphere. In other words, the q squared, meaning the scalar product with itself, is equal to r squared. So what can we say in this case? If we will differentiate this constraint, we see immediately that the velocity is tangent to the sphere. And that's a general geometric fact that if you have a trajectory or if you have a path on a manifold, then at every point of this path, the tangent vector to the path is in the tangent space to the manifold. So so we have this, but now let's look at the action. So it's T1 to T2. We still have the mass. We still have to divide by 2. We still have the square of the velocity. We still have the potential, but now this potential, it shrunk to a function on a sphere. So so now this is function on S2 dt. So we have the same formula, but with the differences that now it's all on a sphere, and then we can do a nice homework, which is the following. Parameterize, use the spherical coordinates for this action and write S gamma in terms of theta, phi, and then you will derive the Newton equation describing the second derivatives of angles theta and phi, but they will be very ugly. So in some sense, this example is a lesson that if we really want to describe the motion of particles on these constrained manifolds, or in general, if you want to have a Lagrangian mechanics on manifolds, then we have to have some tools that are not necessarily involve the coordinate description. And then if we want to do some computations, then we can pass to coordinates. So this will be some function of phi, theta, and possibly the first derivatives. And this will be another function of phi, theta, and possibly the first derivatives. Okay, so you can consider this as a motivational part for studying the Lagrangian mechanics on manifolds. And this is what we will do now. So now we're passing from the Newtonian mechanics. Newtonian mechanics will be a particular example. So now we will develop more general tool, which is called Lagrangian mechanics. And so the main hero here is the configuration space Q. So we assume that it's a smooth manifold. I will recall the definition. Let's assume that it's n-dimensional smooth manifold. So this will be, instead of the configuration space for Newtonian particle or the configuration space for n Newtonian particles. And you can think of this, if you want to think about the configuration space as the configuration space of a constrained system, then most likely you can do this. So, but it's not necessary. What we will do now is we will develop intrinsic description of Lagrangian mechanics on smooth manifolds. Okay, so first, what is a manifold? So typically I would ask in the audience, please raise your hands who know what a smooth manifold is. So, but fortunately in the Zoom there is an option. So please raise your hand who knows what the smooth manifold is. So 1, 2. Oh, most of the people are already sleeping. 3. So Daniil Usov, you don't have a hand. Are you listening? Hello, are you here? Yulia, are you here?
Yes, I'm here.
Okay, good. But you don't know what a smooth manifold is.
Yes.
Okay, so good. That's a great answer. So let me remind what it is. So the easiest thing to, the easiest way to imagine it is that it's a subset in Rn, which is smooth. I'm a little bit vague here. So how do you create subset in Rn, which has a potential to be smooth? You define it as a level set of n minus n functions. For example, you can say q n plus 1 is 0 and qn is 0. So you have n minus 1 coordinate functions vanishing. In this case, qn is just Rn embedded in this very special way into Rn capital. And then typically, these level sets will not be smooth, but let's assume for a moment that it's smooth. Smooth means Qn has a tangent vector, or rather tangent space, at each point. So there is an intrinsic definition. So this is the idea. The intrinsic definition is the following. So in an open, small subset, or rather I should say, okay. In a small neighborhood, of any point, we have n coordinates. Q1, Qn. Alpha means, so we have neighborhood U alpha. So assume we have two neighborhoods that overlap. So then on these neighborhoods, we have two coordinate systems, Q1 alpha, Qn alpha, and Q beta 1, Q beta n. So we can make coordinate change. So we assume that there are smooth maps phi alpha beta that do the change of coordinates, so that Qi alpha is equal to phi alpha beta I Q beta. So, and this is a smooth function. Smooth means infinitely many times differentiable. So Qn, if Qn is covered by these coordinate charts, U alpha, it is a smooth manifold. And we described it intrinsically without any embeddings anywhere. So the basic feature is that, I mean, if somebody, I mean, so if you haven't studied this before, then just read some textbook. But this is the basic thing, that you have coordinate transformations. Okay. So yes, so we have a smooth manifold. And then if X is a point of this manifold, there is something that's called tangent space at this point to Q. And this tangent space is, well, kind of intuitively, it's the following. Let's take the point Q and let's look at n independent path through this point. Or rather, let's look at all possible paths through this point. And this is the span of tangent vectors to path through X. It's a very simple intuitive notion. To give a precise mathematical definition requires some work, but this is a standard work that's done in textbooks, so I'm not going to do it again, but intuitively this is what it is. And then the collection of all these vector spaces, so T, QN, it's an n-dimensional, because our manifold is smooth, so at every point we have an n-dimensional tangent space. So all these tangent spaces, they form the total space of the tangent bundle. So tangent bundle is what it's a projection from the from all the collection of tangent spaces to Q, such that over point X you have the vector space, tangent space at the point X to Q. Okay, so so this CQM tangent bundle to QM is our main object for now. So how can you think of this of elements of the tangent bundle? So this is a collection of tangent spaces. So what's in the tangent space, in the tangent bundle? These are pairs of points, V and Q, where Q is in Q and V is in the tangent space to Q. Okay, so now what is the Lagrangian mechanics? In order to define it, first we have to define the Lagrangian function. It's a function on the tangent bundle with values in R. So physically, it's just a function of velocities and positions. So Q is the configuration space. These are degrees of freedom that our system has. And tangent vectors, these are the velocities with which the system can move. So now for a path gamma, it's a path in Q. Now define the action functional as gamma as integral from T1 to T2 the Lagrangian of Q dot, well, I shouldn't write vector now, sorry. Just Q dot T QT dt. So here, this path gamma, we just write it as QT, T between T1 and T2. So this is a path. And Q dot T, it's an element of the tangent space at the point QT. So this is the most general setup for Lagrangian mechanics. As you can see, the data that define Lagrangian mechanical system is the configuration space and the choice of Lagrangian function. This is where you have to appeal to kind of physics or to mechanics if you want to choose this. I mean, if you want to make right choice of this data. So now critical points of S of gamma. So it's possible to do all these computations with no choice of coordinates. And you know, if you want to be sophisticated, it's a good exercise to do it. But at some point, things will be not better than if you choose coordinates. They will be better in the sense that you will see on the nose that the things are globally defined. But in terms of computations, practically speaking, you always have to choose local coordinates. So I will choose local coordinates. Let's assume that, and from now on, I will be very careful to choose upper indices for coordinates on Q. Let's say that these are local coordinates on Q. Local means on some coordinate neighborhood U alpha. Only Rn has global coordinates. No other manifolds have global coordinates. Like a sphere, it doesn't have a global coordinate system. That's the problem of cartography. You have to remove something from a sphere. You have to cut it in order to have global coordinates. Okay, so then let's just do the variation of S. So I will use the chain rule to the variations just as if I would take the derivatives. And of course, secretly, it means that I have to take the DDS of gamma S of S of gamma S at S equals 0, assuming that delta Q is just d Q T S ds at S equals 0. So I will skip all this and I will just do as physicists do. I will do the small variation of Q. So if I'll do it in the first argument, I'll have to differentiate L with respect to the first argument. And then I have to substitute back V is Q dot T, Q is QT, plus I do the same with the second term. So I'll have the dl dqi vq, same thing. dt. So then again, I will differentiate by parts, and the result is I will have delta qi, and I assume everywhere summation over I, integral t1 to t2, and here I'll have minus ds dl So I'll abuse notations. I'll write it like this. I'll just put q dot q over here. And I forgot I differentiated by parts, so this is also d dt minus, or rather plus, dl dqi q dot q. Integral over dt. But then I integrated by parts, so I have to take into account boundary terms. So it will be delta q it, and then dl dvi q dot q, t equals t1 t2. And so gamma is a critical point. If first Euler-Lagrange equations are satisfied, and Euler-Lagrange equations is what's in here. Critical point means that all directional derivatives are 0. So this is, well, I'll use the beauty of this program, so I'll write it like this. And second, we have to have these boundary conditions. So delta qi t1 dl dvi q dot t1 qt1 minus t1 to t2, that should be 0. And again, you see that if the boundary positions are fixed, if q t1 is q, q t2 is q fixed. In other words, we have Dirichlet boundary conditions. Then 2 is identically 0, because the variations at the boundary points are 0. Okay, so this is the basic idea of Lagrangian mechanics. But you see, I just gave an example of boundary conditions when the boundary terms are vanishing. I didn't explain the concept behind it. And so in order to explain the concept behind it, I think I should pass to the Hamiltonian mechanics, and only then it will be clear. So I will not be discussing it for the time being. So this is more or less what I was planning to do today. Any questions? You know, this is the first attempt. I never taught this class online, and it wasn't quite clear to me what will be the audience, but now it's more or less clear. So, so tell me, was it too trivial, or was it too fast, or was it okay? I need this information to gauge my next lecture.
Since it is slightly familiar material for me, it was all right speed.
Okay. So for those, Yulia, for you, I think some pieces were not familiar. Are you okay?
I like this lecture. It was
good.
okay.
Very good. So, Hauli, was it too trivial? Hello? Hauli? Okay, he stepped away. So, so who is here? Alexandra? Was it okay?
Yeah, it was okay.
Okay, so nothing, right speed or too slow or too fast?
No, it was okay by speed and all was okay.
Okay, good. Daniels? Well, I think we have two Daniels. So how are you doing?
For me, it was fine, but I have listened to the theoretical mechanics course already, so it was all familiar for me.
Okay. So it was, okay, good.
Yeah.
So I see that Hauli replied in the chat. So I'm glad. So I just, I want all of you to stay in the course. So this is why I'm asking. So, okay. So Danilo Usov.
It was okay, thank you.
Okay, good. So then let's. So this will be the end of today's lecture. So next time, the plan was to do the Hamiltonian mechanics, and this is what we will do. So I will say a few more words. We'll give a few more examples of the Lagrangian mechanics on some kind of non-trivial manifolds. I think mostly it's a sphere, maybe several copies of a sphere. And then maybe a Riemannian manifold. I will remind you what Riemannian manifold is for those who don't remember. And then after this, we'll go to the Hamiltonian formulation and we'll move on. Okay. So I'll see you next Tuesday.
Thank you. Goodbye.
Okay, thank you.
Thank you.
Okay.
Goodbye.
Okay. Thanks.
Bye-bye.
Bye.
Goodbye.
Uh-huh.